intrigued me in this work on the quantum foundation is the idea of coherent spectral theory. I didn't know about this thing until this Hishamuddin actually made some abstract, huge series of papers, part 1 up to part 4, which I could not understand till now. Okay, but it's a huge work, and I was confused. Okay, let me learn up this coherent spectral theory, see what it is. Again, since it's a thought, maybe I just do this again. This is some historical introduction, because I was actually speaking to a bigger audience. I thought about how quantum theory works. It's quite interesting in some sense, because the idea of coherent spectral theory was actually, was it 19... It's only in 1967 that was actually discovered. Okay? Now, given that quantum theory was all the way in the beginning of last century, sounds very old, last century. Okay? And the real theory actually is somewhere here, 1945. Okay? And okay, now I'll just use the mouse. Oh. I like to walk around rather than stay. So the real theory of quantum theory is clear. And then being probabilistic theory, people start thinking that okay, maybe we can make quantum theory look like we thought about, okay, can there be some kind of hidden variable that make all these probabilistic predictions, okay? And actually the probabilistic interpretation was actually by Born. It was actually the first, he was the last of the quantum pioneers to receive the Nobel Prize. It's quite late, it's 1940. The rest, almost immediately they got the Nobel Prize. But Born was the last one to get it. Max Born was the teacher of my head of department in the Adelaide, Trevor Green. Born had actually trained Trevor Green quite well, because most of his lectures I could not really find anything in the book. I just had to take several books together. I've done this to most of my students. I take several books just to understand one piece of lecture. Actually, that's very good. Because it keeps you, the formalism, it turns into the formalism is not big, and then you try to start thinking of a bit more broadly about the lecture notes, and just memorizing them. So that's one gave birth to the frame. And so the idea of hidden variables was actually already there in the very beginning. But then one Neumann gave this no hidden variables proof. Okay? And because of one Neumann's authority on many subjects, people start working on it. And those who work on it get very good sometimes. So until perhaps David Bob, okay, who was able to show that okay, there is such a hidden variable and somehow circumvents what one Neumann assumed to be proven. Okay? And I think in some sense David Bob also influenced John Bell to look at possible hidden variable theory. Okay, and then we think of a particular situation for which you have local hidden variable. But that local hidden variables will need to obey certain inequality. I should mention this tomorrow. Okay, Wells inequality, and that Wells inequality gets violated by quantum mechanics. So in other words, that particular result is actually saying there's, not to say no hidden variable theory, it's just no local hidden variable. And then in 1967, quantum Specker, very abstract paper, applied the idea of non-contextual correlation or coloring of waves and found an abstraction. And then essentially that implies the idea of no non-contextual hidden variable. What does it mean by that? It means, I should mention this. And then in 1990s, what is quantum information boom? And in a way, the quantum information boom also gives certain amount of respect to research in quantum information. So people look back to the discussion of quantum nanocomputing. The local, the non-local. You mean the Wells inequality or which one?
Talking about the most earliest derivation of local hidden variables, that would be the first form of contextual.
Well, okay, there is a relationship between contextuality and non-locality, but it's supposed to be a different thing.
Yeah, I'm trying to answer whenever they always use the word contextual versus non-contextual. I'm trying to understand what hidden variables. How do you define that?
Maybe you can run to that question later on, and we'll try to explain as much as possible. So, okay, there are, essentially, for those who are doing quantum foundation, they look for something probably more beyond what quantum theory does. Because there are so many unanswered questions. Now, so here's the idea of the exponential. Again, I'm not going to details because you can find the details in the papers. You have to look it up. Dirty the hands. But just to give you the idea. Okay? So let H be some Hilbert space. Okay, this has more dimension more than 2, and let M be a set of compatible observers. And my highlighting on compatible observers. You know what compatible observers I already mentioned is. Yes, you use compatible observers to actually label the against label the quantum state. Okay, that means your observers have 0, non-commutative. Those are what we call compatible. Non-compatible observers. What's wrong? Why can't we do that? Non-compatible observers, the case of position and momentum. Okay? You know that by measuring position, you actually disturb the momentum. By measuring momentum, you actually change the position. Okay? So these are things that, okay, meaning, okay, it's pretty pointless to talk about to see whether a value exists before that because things have changed when you do the measurement. Okay? But in the case of a compatible observer, it doesn't matter which order you are measuring. Okay? And in principle, there is no, how should I say, there should be no wrong if you actually assume that A and B has values before that. Because essentially, they are not disturbing each other. Okay? So in principle, one can assign values to A, one can assign values to B, because they are not disturbing each other's measurement. Okay? So that's why we have this condition of set of compatible results. So then come the following statement, which is supposed to be contradictory. I should create a set O. Okay? Set O of compatible results. So all members O of M. All members O of M have values. Okay? So meaning you can assign values to this observer, to this order. Okay? Then we have this second statement. Say values of observers A, B, C, and M, any A, B, C, and M, must obey the following condition. If C equals to A plus B, then the value of C must be coming from the value of A and add up with the value of B. If C is a product coming from the product of A and B, then the value of C must come from the product of the values of A and B. Pretty, is that this thing to do? Okay. So, what Cohen Specker says is that these two cannot be paired. Or they contradict. You can find cases for each. So when you say that it's non-contextual, meaning the values are already there before doing the measurement. So it's sort of you just when you do measurement, you just have to figure out what's already there. Okay, and because your measurement doesn't actually disturb the kind of measurement of the other observer. Okay, so in principle, you can meaning now that those values can be non-contextual. It doesn't depend on because it's already just finding out what's already there. So how we go about this is to go to some operators which are simpler in nature. So the best thing to do is actually to work with projection operators. Why? Projection operators are just like doing a logical kind of statement. Let us say yes or no. Or in this case, the eigenvalue is just 0 and 1. Okay. This is R3. The computer doesn't have that. So one work with race, and remember race actually one work with race in R3. Okay, and we can actually, from the race, you can form projection operators. Projection operators 0, 1. And then this race, there are many of them, okay? This race, there are many of them, and you can actually try to start picking some from orthogonal triangles. Okay? One of them will be assigned red. That will be 1. Okay? The other will be assigned blue. That will be 0. So you start to again, I'm not going to detail. You can start to see that, okay, you'll be able to prove that two rays of opposite color, that is red and blue, cannot be arbitrary. So these are the kind of diagrams that Cohen Specker the tool, which is a very complicated thing. They are now simpler proofs than this. So this is not that thing. Only the screen shape thing with this. This one is not. This thing. Okay. So we have this interlocking copies of this picture that we have here in this larger picture. And for this group, finance factor 8, they need about 117 vertices. Just to show that you can actually assign weight and weight, assign 1 and 0. This is a bit complicated. So, most of the physicists are supposed to don't read this kind of experiment. It's too complicated. And there are now simple proofs. So there is, in a way, somebody was disciple of this action. No, that's not the race, trying to find simple. But there's a logic behind it. If you're trying to do some experiment using the origin of finance factor diagram, it would be a nightmare for experiments. So they need a simple. So how to get a simple proof? Okay, you use qubits. Okay, set a two-level system, spin up, spin down. There are 3 different spin observers, Sx, Sy, and Z, given by Pauli matrices. And the Pauli matrices have eigenvalues plus or minus 1. So I forget about the H. Yeah, H power 2. So H only 4. So one just rather than work on this SI, you just work on the Pauli matrices. Information you know the eigenvalues. So you need to work with this medium definition of the finance factor theorem. And sigma x, sigma y, sigma z on its own is not commutative. So you need to work with multiples. So okay, this one is mentioned about tensor product. So you have to put that. So and you get the dimension of the equation. And by the way, okay, actually I mentioned there is a hidden variable theory for 2 dimensions. So the connection with this is essentially you can take this operator sigma. You can find the eigenvectors. Once you have the eigenvectors, you can do the projection. So it's really either you use sigma or you use the eigenvectors. So simplest proof, I think was only this moment popularity. So it does this kind of it looks at 2 qubits, so that means 2 qubits here. So here's an identity operator for qubit 1, sigma z, z component of spin, qubit 2. This one will be the other way around. This will be sigma z for qubit 1, sigma z for qubit 2. And remember that the qubit 1 and qubit 2 we are supposed to be independent of each other. So we should not affect computation. And then one has this arrangement in such a way that along the rows they are compatible. So you can take a commutator of them and equal them in one row. Okay, to give you now, or along the column. And once you have done that, okay, because of the fact that each cell will appear twice. Okay. So now one can actually start to look at, okay, I can do this kind of trick. I can multiply the columns or the rows. So I'll be able to get this kind of relationship. So I multiply this one, the first position, I, sigma z, sigma z squared is I. Okay. The same on the second base sigma z I, sigma z square I, so you get I plus I. Okay? And the same for the rest. So this is coming from the first row, second row, third row, and then this one is actually the column here, column here. So all of this gives you identity on the right hand side, apart from the last one. This is actually giving you a minus sign. Okay? So what's the eigenvalue of identity? Eigenvalue. Identity matrix? One. Okay. So if I start doing the evaluation, I know that on the right hand side, it's always one, apart from the last one. It will be minus one. So I can start comparing the valuation on the left hand side as well. So what I'm going to do, go back to the original page. So that's very good. Saying that you take the value of that, okay, times the value of that, times the value of that, should be equal to the value of that. Yeah, the eigenvalue, plus or minus 1. Okay. But on the right hand side, it should be 1. Apart from this one, it should be minus 1. Okay. So now what happens is, remember that this comes from the either rows or columns. You take any one, say sigma z dot sigma z, that should appear somewhere else as well. Here. So any one element appears twice, right? So if I start doing this, so I think I'm going to skip the one. What I'm going to do is I'm going to multiply everything, right? Multiply everything, and because of each sigma, the sigma that are the one that can have plus or minus 1, but the sigma are appearing twice, so it gets multiplied, squared. So it should be 1, okay? Because sigma squared is 1. So if I multiply all this, left hand side, I should get 1. Because each term appears twice. Okay? And if I multiply the one on the right hand side, right hand side, I multiply this. This is value 1, eigenvalue 1, eigenvalue 1, eigenvalue 1. But for the last one, minus 1. So I multiply all this, I should get minus 1. But the ones over here are all 1s. So you get a contradiction. Okay? So they did it for the eigenvectors as well. And Paris has this 24 rays. Again, the same kind of idea, classifying contradiction. That one is by using multiplication. Here, basically, you're going to do addition. Okay. Addition, you look for even and odd penalty. So from the 24 rays, you start the tetra. This is coming, okay, remember that this is 2 qubits. So you will have to find orthogonal tetrads. Okay. This is orthogonal. Because why you want to make sure that only one of them is actually 1 and the other ones are 0. Okay. And essentially there is contradiction. is a kind of the functional relationship using the principal rays. Okay. So one projection must have value 1 and the rest 0 for each tetrad. But if you try to apply this to whole thing, it cannot be done consistently. So if let's say I put P1 equals to 1 over here, then if it's non-contextual, the other P1s also should be 1. Okay. If it's non-contextual. But it's not possible. Morgan had another one, which is the pentagram. So I asked Carl, how do you get all these different shapes? Why this get all this arrangement of things? There's no particular reason. And this is the ones when I asked him. So essentially, in this pentagram, is along the lines. These are compatible. These are compatible. These are compatible. These are compatible. Again, the same trick. If you use the sigmas, so you use multiplication. You need to obey this thing. And again, it's the same trick. Sigma. The sigmas will apply, will appear twice. When you multiply them, you get 1. But if you multiply on the other side, it's minus 1. And again, Paris did this conversion of sun rule for the case of 3 qubits. So it appears so here 3 qubits, that means the dimension of the Hilbert space is 8, 2 qubits. Right? So you need to find orthogonal of that. Okay? And what we did was, we tried to learn all these things. So we checked the papers one by one. Okay? We checked Kananga and Paris. Apparently there's some mistakes. Okay? So we corrected the mistake. And this, we didn't know. Maybe they are not mistaken. Maybe they're doing some other tricks that we don't know. Okay, but they actually given up this table. Okay, but the idea is good. But beyond that, what we tried to do was actually try to remember that these are projectors. Okay? Project along a particular direction. So we start thinking, okay, maybe we can start doing other tricks like rank 2 problems. It's not new. Okay? People have mentioned about doing rank 2 projection. Okay? Meaning it projects to a plane rather than projects to a line. Okay? And so we did this. Again, we had to make explicit choice to make things easier for us. So this will be a state dependent group. Okay, what we did was to actually do this kind of assignment. Okay, so initially, when we submitted the paper, we said, oh, we have come up with coherent Specker truth with only 8 traits. And then the referee repeated that, oh, you counted wrong. Okay, you need to include all this, the one that is should be assigned. Okay, so in the end, the relevant value assignment that we try to look at is actually this. Some of them is actually rank 2 over here, and we actually try to make a contradictory assignment. Okay, and to satisfy the referee, we actually counted the way we want to count. So we get 1 plus 8 plus 8. So we get a proof of 17 ways. So in the case of the 3. This is according to one particular assignment.
if you do a different assignment, it can be either 17. So we are able to publish that just to give you an idea of how the rates for simple proof comes about. So in the beginning we had ferrets in R3, okay, using only 33 rays. Coherence and some way actually reduced to 31. I was told that this was not published, but they have written some book. And then in dimension 4, let us use 24 rays. And I'm going to reduce it to 20 rays. And finally, Cabello, who's the one doing a lot of work in coherence spectrum in those days, reduces it to 18 rays. In dimension 5, Cabello and colleagues did 29 rays, dimension 6, 31 rays, dimension 7, 34 rays, dimension 8, which is the 3 qubit one. So this 2 qubit, this 3 qubit, then this one will be, what's the name? 5 like 6. No, the one with the 5 states. So we came up with this for 3 and we thought that, okay, we have to one smaller than Cabello. Actually, Cabello did a better proof because it's a state independent one. Okay? And then came UNO in the preprint, 1000 letters. Okay? Just have to be published. They produced a proof with 13 rays. But of course, the 13 ray proof was actually different because this is the kind of, they use Q-trick state. This has kind of rays that they're looking at. And they look at the orthogonality relationship. Okay? And then build up these features that we try to give values on. And they found out that right, it should be this. Okay? Because there's only one of this. H alpha is going to be 1. Okay? But what quantum mechanics in US actually is. So it was actually a coherence spectral proof based on inequality rather than exact. So we try to understand this at some point with the student, what the student finished. We wanted to see, okay, what's the techniques involved. Arendt's, Min and Wempler in computer lab in Oxford actually did a computer proof for R3. Okay? Search for small time spectral vectors. And they were able to, using the idea of square tree graphs, they are able to show that they have to at least contain 18. So that was, they say there was a bound of 18. Okay. So we wanted to understand with respect to this proof by UNO. There was something in that UNO paper that we couldn't understand because the H's that was assumed was not compatible. And I do not know, I think Mambin also was asking the same question, but it seems that the community seems to be accepting this proof. So we still do not know why it actually works.
So what's the issue?
H is, well, H is supposed to be some order. H itself is not orthogonal among them. Okay, the ones that orthogonal are the ones connected by the line.
So that will be like the vertices, right?
The operators are the vertices. So we cannot understand this, and the student left. There goes. So we did not actually try to get things around that because we wanted to do some kind of computer programming stuff. So why the rush for this simple approach is again, they wanted to prove this in experiments. To say that, okay, really quantum mechanics cannot be non-contextual. And
Hordak actually wrote a paper saying that one can actually use, that was the first paper that we saw, one can actually use this contextuality for schematic conditions for QKD. So that was one of the applications. And then there are things also that we wanted to understand from the point of view of logic. Okay? Why quantum theory seems to be having a different logic, and we actually try to understand it within the context of partial Boolean structure. Okay, so that's one of the direction. And Chris Isham and co-workers in the end of Theorem has come with the idea of using generalized operations. So essentially, it's a different kind of logic. This is also coding, settings. This is actually a title of a review of the classification. And also shows it also for one immediately what's in the quick. Because when you do experiments, you actually produce all these things. Very complicated thing you're asking. Shifts are essentially a collection of particles or operators. No, I don't know the technical definition, but certainly it was involves some kind of operators. If operator algebras, I will not be able to say more than that. Okay. Spectral comes from spectrum. So essentially, I wanted to do this kind of talk tomorrow. Okay, but since I have not finished my slides for entanglements, rather than give you an incomplete slide, let me do this whole talk at a time. That's what